right, welcome to the next video. We said we were going to tackle the AB problem from 2013 here. It says, for x's that are greater than 0, find the derivative of the integral from 0 to 2x of the natural log of t to the third plus 1 dt. Now, think about it. If you were to have seen this whole thing a month ago, how freaked out would you be? We have this new symbol called the definite integral. We're taking the derivative of this definite integral, and we're taking the derivative of the definite integral of the natural log, which some students get a little frightened of. But here we know that if we take the derivative of the integral, they're going to undo each other. And I'm just left with the inner function, the integral function, the natural log of something cubed plus 1. But what is that something? Well, it's whatever my limit of integration that is a variable, but then I need to multiply by the derivative of the inside, which is 2. And so therefore, this becomes 2 times the natural log of 2x to the third. That's 2x times 2x times 2x. I believe that's 8x to the third plus 1. And I believe that's going to be letter D. So if you tried 2013 and you got letter D, you are correct. Okay, so now we're going to take what we just learned about taking the derivative of an integral function, of an area function, and we're going to apply all the things we did in Unit 5 with analyzing behavior of increasing, decreasing, of concavity. We're going to put it all together. So here's an example. Let f of x be this definite integral from 1 to x of the function 2t cubed minus 3t squared minus 12t plus t. Find the interval or intervals where y equals f of x is concave up. Okay, where do we begin? There's a lot going on. So we need to interpret the question first. What is it that we're looking for, right? Because if you don't know what you're looking for, then you don't know where to start. Well, I'm looking for where f of x is concave up. This is important because a lot of times students don't look at what it is we're looking for. They see concave up and they know, oh, I have to take 2 derivatives and then I'm done. Kind of, but be careful. We're looking for the concavity, specifically concave up of f of x. So that means that we're going to need to find the second derivative of f, because concavity is related to the second derivative. So step 2 here is I need to find f prime and I need to find f double prime. Okay, well, the derivative of f would be the derivative of this integral. Well, that means that f prime of x is just going to be this function that's in the integrand with the top limit of integration in there. And that's it. That's the first derivative. I didn't even feel like I took the derivative. I'm supposed to multiply by the derivative of the inside, but the derivative of the inside is just 1. So knowing that, can we find the second derivative? Well, sure, the second derivative is just going to be the derivative of this polynomial, which would be 6x squared minus 6x minus 12. Great. Now do the analysis. How do we figure out whether something is concave up or concave down? Well, I got to figure out where the second derivative is equal to 0 and then test points, right? So I'm going to set the second derivative equal to 0. While I do that, I'm going to factor out a 6 from all of these to make my numbers a little bit easier to work with. And now I see that I can factor this out into x minus 2, x plus 1. If you don't know how I did that, we can talk about that individually, but we just factored it out. Why do we do that? Oh, because now we know at x equals 2 and at x equals negative 1, the second derivative is equal to 0 at those 2 points. And I create a little sign chart. For x's, negative 1 and positive 2, the second derivative of f is 0. And now we're going to test points and plug them back into the second derivative. We can plug them into this second derivative, or we can plug them into this second derivative. It doesn't matter as long as we plug it into the second derivative. Pick a point between negative 1 and 2. I'll pick 0. And if I substitute it into this derivative, 6 is positive, 0 minus 2 is negative, 0 plus 1 is positive, and a positive times a negative is negative. I could have chosen any point in between, so all of these are negative. And then I choose another one, like 3. Substitute 3 in here and in here, so that's 6 is positive. 3 minus 2, that's 1, that's positive. 3 plus 1 is 4, that's positive. Positive times positive is positive. And then I'll choose another point on this side, like negative 2. Negative 2 minus 2 is negative. Negative 2 plus 1 is negative. So that's positive times positive, and that's also going to be positive. Why do we need that? Because now we know that the original function is concave up, and then concave down, and then concave up. But the question was, where's the function f concave up? The function f is concave up. F is concave up on x's that are less than negative 1 and x's that are greater than 2. And we're done with this analysis. So think about what we're talking about. We're not talking about this function, because that function would be a cubic. We're talking about the integral of this function, which we're calling f. And we figured out that that function, that area function, that function defined by definite integrals, is concave up on these intervals of x, just knowing what we know about the second part of the fundamental theorem and derivative analysis. Okay. Um, for AB and BC, I don't want you to think that I'm showing you AB and it's not going to apply to BC. These are the type of problems you would see as maybe common questions on both exams. There are some common questions that appear both in AB and BC in the free response. These are the type of problems that could appear as the common question, one of the common questions. So this is an actual AB released, yes? Okay, so step one. Let's read what we have. We're looking at a graph. This is the graph of f. It says the function f is defined on the closed interval from negative 5 to 4. From negative 5 to 4. The graph of f consists of 3 line segments. I can see them, yes, yes, and is shown in the figure above. Let g be the function defined by the integral from negative 3 to x of f of t dt. So I don't want you to freak out. I mean, just because it says f of t, f is the name of the function. This is the graph of this f that we're taking the definite integral. What are we trying to find? We're trying to find g of 3. Well, according to this, g of any x value is the integral from negative 3 to that x value of f of t dt. That means I'm looking for the area under the curve from negative 3 to positive 3. Be careful. There's a 2 right here. And so we're looking for the shaded region here, and then here. Okay, so that's what we're looking for. Well, I can find the area of this right triangle, so that equals, the area of this triangle would be base 3, height 4, so 1/2 base times height, plus, now here, I'm going to play a little game here because I notice that with this line, this part and this part are going to cancel each other out because one is positive and one is negative. So if I can just figure out the area of this little slim part, then I'm done. You can do it different ways. You can look at it as a sideways trapezoid. You can break it up into a triangle and a rectangle, however you want to do that. But I'm not going to include from 1 to 2 and from 2 to 3 because these are symmetrically opposites, and so they're going to cancel each other out. So once I find this, I'm done. I'm going to do a trapezoid. So 1/2 times, well, maybe not. Maybe I'll do a rectangle triangle. Base times height, so base times height plus base times height divided by 2, 1/2, 1 times 2. So, final answer here. This is 6 plus 2 plus 1, and that's going to give me 9. I found the g value, but g was defined as a definite integral. I was still able to figure it out. Okay, let's do the next one. On what open intervals in the in the interval from -5 to 4, is the graph of g both increasing and concave down? So that means I need to, for this part, I need to know where g prime is positive, and then for this part, I need to know where g double prime is negative. So I'm going to have to take the derivative of g twice. Well, g prime is going to be easy because when I take the derivative of this integral, I'm just going to be left with f of x. And when I take the derivative of that, I'm going to be left with f prime of x. I'm supposed to multiply by the derivative of the inside, but that'd be times 1, so I'm not showing that. So when is g increasing? Oh, that's when g prime is positive. But we just said over here that g prime is f. So another way to say that is, when is f positive? So f is positive whenever this graph, which is f, is above the x-axis. So that's going to be from -5 all the way until 2. So that's true for x's that are between -5 and 2. And then